Okay, we're going to start with, oh, maybe not. Okay, so the kinetics review for the IB test. Should I say exam? Alright, so first thing, kinetics, we're going to really be dealing with rates. And what is a rate? Well, the rate of a chemical reaction is really the change in concentration over the change in time. Now this can be the change of concentration for both a reactant or a product. One thing to remember is this is always positive. So you're going to be talking about the rate of disappearance for a reactant or the rate of the product appearing. Remember, the units are moles per decimeter cubed per second. You could also write them as moles, decimeters to the -3rd, seconds to the -1. In the US, it's really molarity per second. Okay. Okay, how would we measure? Oh, have the eraser set. I don't know what this one is. Nope, not that one. Okay, so how would we measure the rate? Measuring the rate of a reaction. We can do the mass or a volume change. And that the mass would decrease if I'm going to generate something like CO2, a gas. Okay, the volume, we could look at the volume of a cylinder that's able to move to maintain atmospheric pressure if we're again generating a gas, and this should be or volume change. Okay. We could look at the change in conductivity if the reaction system is going to be changing in the number of electrolytes. Okay, but you've got to have some electrolytes for that. We could look for a change in the pH. If we have an acid-base system and the concentration of the acid is going to be changing, we could also look at using a colorimeter if we are going to be changing the color of the solution, right? And remember, when we're looking at the rate, we're really going to be looking at some change over time. If we're going to be looking at the volume of CO2 produced, you would get, or should get, something of a curve like this. Remember, the rate is, we're looking at instantaneous rates. You want to draw that tangent to the line. I'm having difficulty with that. But the rate here is going to be equal to the change in volume over the change in time. And that can be equal to the slope, and you get the rate at that particular point. The other thing that we might be able to do, again, is to look at the change of, say, the mass of the flask if we are generating a gas. Okay, and that would go down, and again, we could look at that for the instantaneous rate being the change in mass over the change in time. Remember, there is a difference between instantaneous and average rate. Reaction kinetics are really determined by collision theory. Remember, there are 3 important points in the collision theory, and they are particles must collide, They have to collide in the right orientation. And they have to collide or collide with enough energy. And I'm hoping that the term activation energy kind of popped into your head. Right, so let's take a moment and talk about activation energy. Okay, and this is really the definition, the minimum So the Maxwell-Boltzmann curve, if you remember, we are looking at kinetic energy on the x-axis and number of particles on the y. There should be an R in there, particles. Okay. And what we look for is this. And remember, this is the one where you cannot draw this to the line, otherwise they take points off. Okay. So don't go to the axes on this one, because you'll lose marks. All right, your average kinetic energy is somewhere here. Okay, and what you're looking at for any sample of gas, the area under the curve is going to remain constant. So you're really looking at the number of particles in some sample and what their kinetic energy is, how many particles are at each different kinetic energy. All right. If we were to draw the curve for a higher temperature, it would be flatter, okay, and this is at a higher temperature. Your average kinetic energy would go be higher, okay, and you hopefully can see that we've added many more particles at a higher kinetic energy. Taking just a real quick look at that, let's add another piece to this, and this would be like the activation energy. Okay, and you can see that making the temperature higher, I get more particles that have enough energy to produce it. I thought I bought this. Okay, all right. So, I want to go back to yellow. That way I feel like I'm writing on an old-fashioned chalkboard. All right, so what kind of factors can increase the rate of reaction? You can increase concentration of the reactants. Increasing the concentration of the reactants would drive the number of collisions up, total number, both effective and not effective, but if you drive all of them up, you're going to increase also the number of collisions that are effective. All right, so increasing the concentration increases the number of collisions. You can increase the temperature, and this actually does two things. Okay, of a smaller effect, is increasing the number of collisions, but that's smaller. The greater impact is increasing the number of particles with the sufficient energy. Okay, and that we saw on that Boltzmann diagram, and that's really what you're doing here by increasing the temperature. you can decrease the particle size of a solid reactant. Okay, and then decreasing particle size of a solid reactant. And really, what you're doing is, say you have a big chunk of your solid reactant. You only have these surfaces where the reactants can collide with that big chunk. If you were to cut that down into smaller chunks, okay, you've got many more surfaces for that to, because remember, you have to think in 3D. You have more surface area along those solid particles for the reactants to collide with the right orientation and with enough energy to actually make the reaction happen. All right, so increasing the particle size of a solid reactant does increase the rate. And one thing to remember, okay, your mass is really the same. You're just making smaller particles of that. Okay, and then another thing that's going to increase the rate would be adding a suitable catalyst. That's adding a suitable catalyst. Okay. And if we look at this enthalpy diagram again, this would be pathway. Normally your EA is here, activation energy. By adding a catalyst, really what we're going to do is just add or provides an alternate pathway for the reaction, and that would be your EA with a catalyst. So you're lowering the activation energy by providing a different pathway. I think that I will stop here, and the second screencast will cover rate equations, graphical representations, and mechanisms.